In the 3 minutes because you can't weigh it hot, so you got to touch them, right? Makes sense to me.
You know, so what we're trying to do is we're trying to prevent the chem lab be like, you know, the Darwin Award is a failure thing. You know, we want you to make it through without any life long injuries.
It's a chem lab, not a kitchen.
It's not. It's not the Hunger Games. Okay, all right. So I guess it's time to start, and the internet is running again. So we do not have to go back in the day.
Chalk and talk.
Chalk and talk, yes. The phrase of the day is chalk and talk, children. Okay, so this is where we left off. So we were talking about oxidation states. So oxidation reduction means it's a chemical reaction where you have an exchange of electrons. So that's what oxidation reduction reactions are. And there's a way, how can we keep track of where electrons are going? One of the ways we can do it is by using oxidation states. And these are a real thing. The oxidation states of elements matter. So to give you an example, chromium. So chromium in its zero oxidation state, it's a metal, it's safe. Chromium plus 3, sometimes referred to as trivalent. So plus 3 chromium is also completely safe. You can put it in glass, and some glassware, you can put it in paint on the walls. And then there's chromium plus 6, also known as hexavalent chromium. This stuff will give you a skin rash and give you cancer. So it's a big deal. Like if you've seen the movie Erin Brockovich, that's the stuff. It's chromium plus 6. So anyways, let's go through this the rules again. So it's not because it's not on the board. We're in the age of electrons here. So the rules are oxidation state of an atom at a free element is 0. For a monatomic ion, so one atom ion that's charged, for the sum of oxidation states in a neutral formula unit is 0. An ion equal the charge of that ion. Alkalis are +1, alkyl inerts are +2 in compounds. And then for all else, we have this chart given here. Okay, so, and we went through the example. Let me show you the oxidation states in potassium dichromate. So this is the cancer-causing Erin Brockovich stuff. And it's kind of interesting. This stuff is the best way I can describe it is a minion yellow. So it's a very, very bright yellow compound. I took a sculpture class at UH Manoa because I get free tuition. And I remember that they had potassium dichromate there. And the artist had no idea how gnarly that stuff is. It's really, really bad. But I actually made a minion. I thought about turning it with potassium dichromate, but I changed my mind and made it light pink, light blue instead. I used copper. Anyways, but potassium dichromate, what are the oxidation states? So the sum of this, it's a neutral unit, so 0 is equal to 2 times potassiums. So 2 potassium plus 2 times chromiums plus 7 times, and I'm just doing OX for oxygen because my O's look like zeros. And where am I getting this from? 2 for the potassium, 2 for the chromium, 7 for the oxygen, and this all sums up to 0. So now let's look at potassium. Potassium is an alkali. Potassium is going to be +1. And from the chart, if you recall, oxygen tends to be -2. So we can plug these in now. 0 equals 2 times +1. You don't have to put the +1, I'm just doing it for emphasis. Plus 2 times chromium plus 7 times -2. And 7 times -2, this is -14. 2 times 1 is 2. So so we have 0 is equal to 2 plus 2Cr -14, or 2 chromium equals 12. Chromium is equal to 6 plus 6. So it's +1 plus 6 -2 for the oxidation states here. So questions on how I'm doing this?
So wait, Cr has no charge?
Is that because it's a
+6.
transition, so you had to calculate it that way?
Yeah, yeah. and and it's bound by the potassium K and the oxygen O.
So we're just trying to balance the electrons.
Yeah, so the chromium is very electron poor. So this chromium, the chromium in this compound does not have many electrons around it, whereas oxygen has a bunch of electrons around it. Question?
The reason why you didn't do the chromium thing, is that because of those rules that you showed us?
Yeah. The rules are hierarchical, right? So I mean, one is more important than two, right? So we went to rule number 3, where we have a neutral molecule is 0. The sum of the states is 0. That's what we did there. And then we did this rule here because potassium is an alkali. And then we did this rule here for the oxygen B minus 2. That's the order that we went in. And chromium is not on here, so we had to solve for it by using the equation. Using this equation here. Does that make sense? Okay, let's see if you can figure out what the oxidation state in manganese is in potassium permanganate.
Okay. Challenge accepted.
This stuff is interesting. It's very purple. I'll give you a start. That's a 0, not a 6. Would have blurred out the answer. I'm giving you guys hints if you're getting stuck.
I know, I didn't even see that till after. Could save me some seconds.
Could have.
It's starting to click.
I need to get my flu shot. Well, it's because when they came out, I had ear infection, and you're not supposed to get vaccinations when you're sick already. All right, how many people think it's A0? I think it's B7. How everyone's going? Is anybody? Are you guys stuck? Do you know? Do you understand it or okay? Good, you guys are. This is awesome. Actually. No, I'm really happy. You guys are doing very well.
Thank you.
So +1 plus manganese plus 4 times -2. So this is -8. So that means 7. You get 7 equals manganese. So or 0 is manganese -7, and it goes to. Anyways, I'm mumbling. Mumble. Okay. Moving on. So, identifying redox reactions. So, students also have a hard time with this. So, I'm going to do a little bit of acting in a way. The concept I want to tell you about is oxidizing agents and reducing agents. So, it's a little confusing because whatever is oxidized is actually the reducing agent, and what is reduced is the oxidizing agent. So what I mean by that is kind of like it's the opposite, but it makes sense. So, but when I think about this, I always think about James Bond. I like James Bond movies. You know, he delivers lots of death. He's always delivering death, but he never dies. I've seen lots of James Bond movies. I've seen him get beat up a lot, especially the new one. He's gotten beat up quite a few times, but he never dies, right? So, but he delivers death. So instead of death, we'll call my water bottle an electron. So I'm a reducing agent. I have an electron. So I'm a reducing agent. That means I deliver reduction. I deliver reduction. I've delivered electrons to the table. I've reduced the table as I'm a reducing agent, but I lost electrons. I have been oxidized, right? So I've been oxidized, I've reduced that, and I'm a reducing agent. Now, I'm an oxidizing agent. So I oxidize things, and I look at this, so what do? I take the electron. I've oxidized the table. What happened to me?
You got reduced.
I got reduced. I have an extra electron. I am reduced. So if you follow that. So whatever is oxidized, whatever is being oxidized is actually a reducing agent. It's delivering reduction. And whatever is reduced is the oxidizing agent. So, okay, let's look at this equation then. So we have magnesium plus 2 waters makes magnesium hydroxide and hydrogen gas. So let's look at the oxidation states. Magnesium is a free element. Its oxidation state is 0. Water, by the compounds, hydrogen's +1, oxygen's -2. In a compound, magnesium is an alkaline earth, it's +2. Hydroxide still -2, +1. And then hydrogen is a free element. Its oxidation state is 0. So what happens here, magnesium is oxidized. It goes from 0 to +2. So it's lost 2 electrons. And hydrogen here has gone from +1 to 0. So each of the hydrogens have gained an electron. So what happens is, in this chemical reaction, magnesium is giving 2 electrons to water, and then the hydrogens take the electrons and then bubble off as gas, and then magnesium becomes magnesium ion and hangs around or in solution with water, or it precipitates out. So that's what's going on in this chemical reaction. Magnesium is giving electrons to water. So magnesium is being oxidized. It's the reducing agent. It's delivering electron density. It is the reducing agent. It is being oxidized. Water is the oxidizing agent. It is being reduced, but in doing so, it is forcing the magnesium to become oxidized. It's delivering oxidation to the magnesium. Is this making sense? Okay, I can't read your faces. You're looking at me kind of like, huh? Give me some sort of verbal feedback. Are you following the logic? Maybe, kind of, sort of, maybe halfway. Okay.
Halfway.
Halfway. Okay.
Do you always write the reducing agent first?
No. Well, let me test you and see how well you understand. We have glucose plus oxygen makes water and carbon dioxide. Riddle me this. What is the reducing agent?
So that gets oxidized.
So how many people think it's A, glucose? How many think it's B, oxygen? Okay, I'm going to give you a hint. It's not C or D. Those are products. It has to be a reactant. So it's A or B.
A.
So let me give you some numbers. Oxidation state in carbon in here is 0, +1, -2, 0, +1, -2, +4, -2. So what's going on here? What's going on here is that the carbon in glucose is losing 4 electrons. And then the oxygen is gaining.
So they're getting oxidized, the carbon.
So which one is the reducing agent?
The glucose.
Yeah. How many people think A, glucose? Okay, well, you're still both right. Yeah. Glucose is the reducing agent. So it is being oxidized. So you understand that carbon here starts at oxidation state of 0, and then it goes to an oxidation state of +4. So you understand that from going to 0 to +4, that means it has 4 electrons less around it. Yeah.
So thinking of it in simpler terms, so going from a 0 to a plus charge is the reducing agent, and then going from a, is it a plus to
A
zero?
negative.
Negative.
So going up in positive numbers makes it a reducing agent. Going down in positive numbers or in a negative or more negative makes it an oxidizing agent. If you were using your words or your analogy.
Yeah, because the last one was like 0 to +1 and
Yeah.
+2 to 0.
Yeah. Correct. So if you didn't know that, there's a couple ways you can find out that this is the reducing agent. Do you remember what I told you the most common reducing agents were? Do you remember what they were? Fuel. Fuels are the most common reducing agents. And glucose is a fuel. Oxygen. So what is the most common oxidizing agent? Oxygen. So if this is the most common oxidizing agent, that's probably a reducing agent. And how do you know it's oxidized? Well, one of the definitions is adding oxygen to something is oxidized. You are literally adding oxygen to it, a plus O2. You are adding oxygen. Right? So that's another telltale sign that this is being oxidized. So this is being oxidized, therefore it is a reducing agent. Is that making sense? Do I need to explain it? The morning class wanted me to explain it like 4 or 5 times. And I mean, it's okay. Are you guys getting it, or do you want me to? Should I do another?
Does it being a free element, the oxygen over there, does that have?
That has to do with assigning the oxidation states. So this just, a free element just means that the oxidation state is 0. It means it has all of its electrons. So a positive oxidation state means that there's a lack of electrons that it normally has. An element has all the electrons that it normally has because it's an element. And a positive oxidation state means that the element is missing some electrons. And a negative oxidation state means that the element has more electrons. Yeah. So, and then it comes to what a reducing agent is. A reducing agent is something that gives electron density. I'm a reducing agent. I am very generous with my electrons. I, as a reducing agent, am very proud to give you my electrons. So that's glucose. Glucose is, oh, hi, oxygen. Here are my electrons for you. And I'm a reducing agent, and I am happy to give you my electrons. And oxygen is like, my electron. I'm an oxidizing agent. I've oxidized you. So that's what happened.
Can we do another one?
Okay. Easy one or a hard? Okay, I can look in the book. I wasn't prepared for this. I could make one.
Make sure it clicks.
What's that?
We want to make sure it clicks.
As you wish, you are my clientele. Okay, are there any questions? Okay, they don't have. Nope, those are not good questions, but I can always make things up if I have to. Oh, here's some. Alrighty. On focus.
high tech.
Okay. So let's start with A. And lithium looks pink when you burn it. So lithium, it's a free element. What is its oxidation state?
0.
0. Chlorine, free element. What is its oxidation state?
0.
And a compound, lithium, it's an alkali. What is its oxidation state? It's +1. And chlorine, this is the neutral unit. That means chlorine is -1. It's also a halogen. Halogens tend to be plus or -1. So you get that free element oxidation state 0, chlorine oxidation state 0, lithium is +1. It's in a compound. It's an alkali. Chlorine is -1, and lithium chloride. Okay. So who is losing electrons, lithium or chlorine?
Lithium.
Lithium is losing electrons. It's going from 0
Positive.
to +1. It's losing electrons. Chlorine is gaining electrons. Lithium is being oxidized or reduced.
Lithium is getting
Oxidized.
so it's a reducing agent.
This is This is being oxidized. This is reduced. This is a reducing agent. This is an oxidizing agent. Also can be called an oxidizer. So if you want to call it an oxidizer, you can call it. You can see that on trucks. You go by, it says like oxidizer. I guess there's not too many trucks here though. On the mainland, there's lots of trucks. Okay. Questions on this one? Okay. Yeah, nothing happens. That's a no reaction. Won't confuse you. Here we go. So, aluminum, free element. I'll do blue. Aluminum oxidation state 0. Tin, it's +2. Aluminum, +3. Tin, 0. So, aluminum goes from 0 to +3. Is it being oxidized or reduced? It's being oxidized. It's losing. Going positive means losing electrons. So if this is being oxidized, what does it make it? It's the reducing. Yeah, of course. This is the reducing agent because it is being oxidized. It's delivering its electrons. It's delivering reduction. Tin goes from +2 to 0. It is absorbing electrons. It is oxidizing this. It is the oxidizing agent by the fact that it's being reduced. Make sense? Okay, for the last one then. These two are 0. And if you remember from that, this is +4 -2. So carbon, is it being oxidized or reduced? It's being oxidized.
Yes.
Right, so carbon starts at 0, it goes to +4. Oxygen starts at 0, it goes to -2. Yes?
For a thing like that, is it ever possible for them? This is a stupid question, but the carbon can't ever be the oxidizing agent.
It can be.
It can?
Yeah.
Okay. That was a dumb question.
No.
Oxidation, oxygen.
Is it carbon -4?
It can be.
+4?
You can.
Is that one that's like either or?
You can have 2 calcium metal plus carbon can make calcium carbide.
No, I mean like just if oxygen's on the left side.
Oh,
That's always the oxidizing.
yeah. I guess and from I think you asked question. It does seem like the reducing agent usually is first.
That's what I
Yeah.
saw. 'Cause it's pretty
And I even wrote this with the reducing agent first as well. I don't know.
Just an unsaid rule.
It could be, but it's not it's not a hard rule. You frequently,
Just proper.
yeah, you frequently put the things of lower electronegativity on the left and the higher electronegativity on the right. We haven't talked about electronegativity yet, but that's another thing. And electronegativity is the ability of an atom to draw electron density. So the things that have higher electronegativity tend to be the oxidizing agents, so they're further on the right, and then the lower ones tend to give off more electron densities on the left. But I mean, there is not necessarily any reason why you could put carbon first and then calcium. That is not improper, but it is more customary. I guess it is more customary to do that. But I wouldn't rely on that rule though.
Just on a test, if you had to guess.
Sure, if you
Didn't know.
Who wants to be a millionaire? Go for it. Other questions? Is this good? Do you need more examples, or is this? There's not too many more. Okay.
I think that was good.
Alrighty then. So we are done with the testable thing. So the test is a week from today, and on Monday I'll do a review, and before then I'll write the test so you can ask me questions. I haven't written it yet. So, and I'll tell you more about the conditions of the test as well. I'm considering doing it open book, but the problem with that is that the test is going to be harder. So, but I'm trying to run this parallel because the online course, I mean, it's an online course, of course, is open book because they're not a testing center, so they have access to everything. But anyways, that's just in my mind. Do you want it open book or do you prefer it closed? Okay, well, I'll think about it.
Well, closed book if you're gonna make it easier. Still a cheat sheet, yeah.
No, what if we just have like a little cheat sheet instead of having an open book, just like
Like a cheat sheet.
A crib sheet or what they call it? Yeah, I see your point.
but don't make it as hard as like you'd want to.
Oh, we're negotiating. I
like someone
Oh.
compromise in the middle.
Can I have a pony then? If we're negotiating.
I'll get you a unicorn after.
I didn't even think of that option. Okay, so you're saying so you want me to still provide you with all the nodes, or the important equations and the constants, but then you can have a crib sheet.
Just one side.
But a crib sheet, I guess a crib sheet is a good way to study though. That is an active.
Study by writing it.
Yeah, that's an active form of learning. So that is something. Let me think about it. Okay, let me
Ferment on that.
Yes, ferment. I will ferment on that among other things. Okay, so what I'm going to talk about right now is not on the
Look at
test.
that guy lying down.
It's a drowning. Yeah.
He's drowning.
It's drowning. Come on, my artistic talent is limited. Okay, so this is not on the test on Wednesday.
Okay.
Okay, but it is on a following test. Okay, and this chapter deals with gases. So we deal with gas laws. And question here, instead of scuba diving, what if I just had a really long snorkel? Would this work? Say I swam 100 feet underwater and then had a really long snorkel. What would happen if I tried to breathe? Could I breathe, or would this not work?
No. You have too much carbon monoxide in it.
Not carbon monoxide, but what would happen if I tried to breathe? Well, let me give you a hint. 100 feet of water, so at sea level, there is 1 atmosphere of pressure. 33 feet of water. This equals the same thing as an atmosphere of pressure. So this 100 feet, this is the same thing as 3 atmospheres of pressure, which means that the person's lungs has a pressure of 4 atmospheres.
Is it just like a linear scale of atmosphere? It's not like a,
What do you mean?
like, it's every 33 feet it adds on another atmosphere?
Yes. Because liquids tend not to be compressible.
Yeah, that's right.
So in the atmosphere, At sea level, it's an atmosphere, but as you go up, it's an exponential decay going up. So, but underwater, it is linear, more or less. There's a little bit of compressibility, but it's more or less the same. Okay, so that means that someone underneath 100 feet of water, the diver has a pressure of 4 atmospheres in his or her lungs, and then ambient pressure is 1 atmosphere. What's going to happen when the person tries to breathe?
Suffocate.
Well, lungs will collapse, but yeah. The pressure, or when things flow, so why do things flow? Things flow because of entropy, because of disorder. It's always from high pressure to low pressure, from high temperature to low temperature, and from high concentration to low concentration, right? You don't, so when you put your ice cream in the oven and you turn on the oven, the ice cream doesn't get colder and the oven gets hot. The ice cream's not going to give its heat to the oven and warm up the oven, right? The heat's going to go from the hot oven to the cold ice cream, right? It's going to melt the ice cream. So temperature always goes from high to low temperature, high to low pressure, right? So if I have a pressurized gas cylinder and I open up the pressurized gas cylinder, all the air in the room is not going to rush into the cylinder and get higher pressure, right? No, the high pressure is going to come out of the tank. So flow always goes from high pressure to low pressure, and thing with high concentration, low concentration. If there's a smell of flowers in the room, if I put an empty bottle in there, all the flower smell is going to go in the bottle, right? No, right? It's the opposite. If I have perfume, which is concentrated smells, if I put that and I open it up, the perfume is going to go around the room. Not the opposite. We don't go from low concentration to high concentration. You always go the other way.
So, because his lungs are low pressure, all the air is just going to come into his lungs.
It's high pressure, 4 atmospheres.
He's got the high pressure.
Yeah. Yeah, underwater, you have the pressure from the atmosphere plus 3 atmospheres from the 100 feet of water.
So his lungs collapse.
Yeah. The air is going to go right out of the lungs because it goes from high pressure to low pressure. And what is that? What is pressure? You probably feel a little bit of pressure right now. Pressure means force per area. So definition of pressure, if you're feeling, I feel lots of pressure. Force over, yeah, A is area. So pressure is force divided by area. And a common unit of pressure that we use in for air and tires is PSI. What does PSI stand for?
Pressure.
Pounds per square inch. So a pound, so a PSI is a force of a pound. So this is about a pound, and over an area over an inch squared. So 1 pound over a square inch, that's 1 PSI.
That's imperial though.
Yeah.
Metric.
Mm-hmm. Metric, the unit for metric system, we use Pascal. A Pascal is 1 Newton, the force of 1 Newton over a square meter. So a square meter is about this big. So this is about a square meter. And there's about a liter of water in this. A liter of water is about a kilogram. Well, it is a kilogram, sorry. It is a kilogram. And this is physics, you don't have to know this. But the weight of this 1 kilogram of water, and weight is a force. Here on Earth's gravity is 9.8 meters per second squared. So mass times acceleration is the force. This is about 10 newtons. It's 9.8 newtons, but about 10 newtons. So the pressure of a Pascal would be if I poured about 1/10 of the water and put it evenly over a square meter. I mean, even the surface tension of water would beat up, but that's how weak a Pascal is. A Pascal is not a very high pressure. So, we'll talk about pressure units later, but it seems like you're interested in them now. The one that we use quite a bit in this class is an atmosphere. That's the average pressure of the Earth at sea level. And we're more or less we're at like sea level plus 5 or 10 feet right now. So we're pretty much at 1 atmosphere. So, where does this come from? Where does the pressure come from? It comes from the weight of the air. Okay, so from here up to about 60 miles is what we consider, up about 60 miles straight up is what we consider to be outer space. So if you take the weight of every single gas particle as it goes from 60 miles up all the way down to the surface of the Earth, all the way to that by gravity, that is equal, that the amount of weight on us from all that air, and it's 60 miles of air, but it's not an even spread. But that's the same thing as 33 feet or 10 meters of water. So 10 meters of water is about the same amount of force as the entire atmosphere pushing down on you at sea level. And also 760 or about 29 inches of mercury. So about this much, a column this high of mercury is the same force. It's the weight. So if you ever wonder how much the atmosphere weighs, at least coming down on you, it's the weight of it. It would be about this much mercury or 10 feet of water. So, okay. And gases, so we're talking about gases. Let's pretend that there's gas in this instead of, there is gas, there's air. Let's say it's pressurized. Say I've got something like propane in this. And it's going to be pressurized, it's under pressure. Where is the pressure coming from? It's coming from the gas particles, the molecules, hitting the sides of the container. So one gas particle hitting the side of the container, not a big deal. Molecules don't weigh very much. But if you have a big number of them, I don't know, like 6.02 times 10 to the 23rd of them, suddenly all those collisions, every single gas particle has a little bit of momentum. It's pushing on it in the collision. So if you have a huge number of them, then the whole thing, you can feel the pressure. So it's not just one, it's many, many, many hitting the side of the container. So, another thing with pressure, sound waves, these are pressure waves. So when you hear sound is actually also known as a longitudinal wave, and a shock wave is also a longitudinal wave. So have you ever seen videos of explosions and the shock waves coming out? So that's a pressure wave, that's a pressure change. And how sound works is it's a pressure wave through the air. And as I'm talking to you, the air particles, they're moving back and forth. So as the sound is moving towards you, the particles in the air are moving back and forth in the direction of where I'm talking. So that is when you have the displacement, the motion of the wave is the same direction as the particle is moving. That's known as a longitudinal wave, right? So if a bomb goes off and I hit the shock wave is coming this way, I get blown back, right? I get blown back in the direction of the wave. Ocean waves, they're known as translational waves because displacement is perpendicular to motion. So an ocean wave is coming, so you're sitting here floating in the ocean, and a wave comes, what happens to you? You go up and down, right? You go up and then you go down. Your motion is perpendicular to the wave is moving this way and your motion is this way. That's called a longitudinal wave. Light is a longitudinal wave. I'm sorry, transverse. Light, so motion this way, displacement perpendicular to the motion, that is a transverse wave. Light is a transverse wave. We'll talk about that in 2 chapters from now. But sound is a longitudinal wave, and it's from the change in pressure. Okay, so I'm going to build up, and anybody have any questions? No. All right, I'm going to build up and talk about the gas laws. I'm not going to go through it in painful detail like the book, but I'll give you some basic concepts. Start off with Boyle's law. Boyle's law says that pressure and volume are inversely proportional. Inversely proportional means when one goes up, the other one goes down. And if one goes down, the other one goes up. So they go like this. So they do the opposite of what the other one is doing. So pressure and volume. So if I blow up a balloon here at sea level, and I have a balloon, what happens when I drive the top of Haleakala where there's less pressure? Does the balloon expand or contract?
Gets smaller.
No,
Oh, no.
It gets bigger.
It's bigger.
Yeah, the pressure goes down, the volume goes up. So I think of this kind of like my bank account balance versus how much fun I'm having. If I'm having lots of fun, what am I doing? I'm taking
Spending a
trips.
lot of
Yeah,
money.
man. It's fun to spend money, right? You can go shopping. Shopping is fun. You can go out to eat awesome food. That's fun, right? Take trips. I love taking trips.
You're
That's
on that
fun.
professor budget though.
Oh yeah, you know how much
More
those
money.
teachers make, you know. But actually, no, I'm certainly upper middle class, but I'm not, you know, wealthy. But anyways, so if I'm having lots of fun, my fun level goes up, my bank account balance is going down. So let's say I want to bring my bank account balance up. What am I going to do? Well, I'm going to start working more. I'm going to start staying in and watching Netflix. I'm going to start eating ramen noodles and crock pot meals, and my fun level starts going down, right? So they are inversely proportional. How much fun I'm having versus my bank account balance. So, and that's pressure and volume. So when the pressure goes up, the volume goes down. And if the volume increases, the pressure decreases.
Isn't there also a temperature along with this, or is that a different thing?
For Boyle's law, no. For other law, pressure and temperature, you mean? That's Gay-Lussac's law we're not talking about.
I'm thinking of there's as pressure and volume. Pressure goes up, but volume decreases. Temperature also goes up, or something like that.
In this case, you would hold temperature and the number of moles, gas constant. But you can combine them with a combined gas law, which we're not going to cover, but then we're going to work to the ideal gas law, where that you can get several different cases in Europe. So, all right, moving on. Charles' law. Charles is his law. So Charles' law says that volume and temperature are directly proportional. And we don't have hot air balloons here, but hot air balloons work off that principle. So if you've ever seen a hot air balloon, what they do, you start off with a real droopy balloon, and then they light a fire, and usually it's a gas torch, but they light a torch under the hot air balloon, and what happens to the droopy balloon? It gets nice and big and full, and then it starts to float. Why do hot air balloons float? It's because it works off of something called buoyant force. So you can float in water, and the reason why you float in water, and like when you float in water, you're like up to your neck, or you're up to your upper chest, right? And the idea is whatever's underwater, the weight of the water that you're pushing away equals your weight, and then you float to wherever it is. So same idea with ships. So if you have a boat or a boot, if you're in Canada, no, that's a bow, never mind. Like if you have a ship, there's a certain part that's underwater, but the amount of water that ship is pushing away equals the weight of the ship, and then it floats to whatever level it cools out at. And that's called buoyant force. So when the hot air balloon opens, by buoyant force, it'll rise until the atmosphere gets thin enough and it'll stop rising. Okay. So, so Charles' law is directly proportional, and I jokingly say that's like your grades versus my happiness level, right? So when I'm happy, I'm a very easy grader, and everyone's getting good grades. And when I'm really sad and angry, I take it out on you, and then your
It's
grades.
not fair.
I'm joking.
Go home.
Go home. Take some happy pills. I want my A, yes. Okay. And Charles' law also has to do with absolute temperature. So I should probably define temperature. So temperature, the definition of temperature is average kinetic energy. So that's what the book will tell you. Let me go beyond the book and explain things a little bit more in depth. So temperature is really average translational kinetic energy. So let me explain this to you this way. So right now, I am moving very translationally. This is my translational motion. How else can I move? Can I move any other way? No one wants to ask. I can twirl. This is called rotational energy.
Would it be different if you did a handstand?
No, that could still be if I did twirl in a handstand, I don't have that level of balance. And I don't want a concussion either. And so I can twirl. Is there anything else I can do? I can just, what?
Jump.
I can
Off a cliff.
jump off a cliff. Man, this is,
I was just,
these subliminal, I'm not getting a lot of aloha here. These subliminal mentions like,
I was thinking like horizontally.
man. All right. Any other suggestions? Before I jump off the cliff, apparently. I can dance. I can vibrate. So think instead, okay, Shaka, yeah, but think about a water molecule, hydrogens and oxygen. So temperature is translational energy. This is temperature. So when you have like hot water and cold water, there's a difference between hot water and cold water. What's the difference? This is cold water, this is hot water. The molecules are moving faster. And what? So if you ever wondered how your microwave oven works, microwave ovens work by making water molecules rotate. So microwaves make water rotate. And what's happening is the water is already moving around, but it starts to rotate. And then when it collides, so it has a slow water, and then with a collision, it turns this rotational energy into translational energy. So now, that by rotation and by collision, then the water starts getting warmer. So that's how a microwave oven works. And you can get warm also by a fire. Fire gives off infrared light, so does the sun. So if you're cold, you go out in the sun, or you stand by a fire and you feel the infrared light. What does infrared light do? It makes it vibrate. So you have so it's probably easier here. Oxygen, hydrogen, hydrogen. It makes the water go like this. And then as it's vibrating and it hits another water molecule, it transfers that vibrational energy into translational energy, which is temperature. So when you feel the heat of the fire and it's warming you up, it is making your molecules vibrate, and then when they hit each other, then it turns into temperature. So on a molecular scale. So that's what temperature is. Average translational kinetic energy. Yes?
Speaking of temperature, yesterday Dr. Fisher asked us why things weigh more when they're colder than when they're hotter. Do you know the answer to that question? He looked it up later, but I'm just wondering if you know.
Things weigh more when they're colder? Because they
Well,
contract.
like the crucible, he said to let it cool completely before you weigh it because the weight would be different based on the temperature.
It expands. So I mean, materials, generally speaking, liquids and solids don't expand very much, but they do a little bit. And if it expands, then there's buoyant force because it pushes air out of the way. So a colder crucible, if you have enough, it'll weigh more. There's other reasons why. I'd be surprised I could even measure that. But moisture is the other thing. So if you have moisture in it, if you heat it up, it's going to burn off all the moisture.
What it said online for him is said it was something about more kinetic energy or something like that in it.
Yeah, so it'll expand.
That's why I had to keep touching it to see if it was hot before I weighed it.
Yeah, but as you're touching it, you're also adding your oils. So you're increasing its mass. So it's air, experimental air. Okay, so going back to temperature. Temperature is motion. So on a translational scale. Okay, so what about when you're not moving? So things are moving. What happens if they absolutely stop? So when they stop moving,
Zero temperature.
that's zero temperature. That's absolute zero. So you can't get any colder than absolute zero. Absolute zero is the absolute scale. And the unit that we use for absolute zero, or absolute temperature, I should say, is Kelvin. And Kelvin is degrees Celsius plus 273. So, and notice that you have degrees here. A degree means it's related to something. The scale is a relatable scale. Kelvin is an absolute scale. You can't go colder than 0 Kelvin because you can't go any slower than not moving, right? So that way, but if you see degrees Celsius, if you say, oh, what's the temperature outside? Oh, it's about 30, it's a hot day, it's 30 degrees outside, it's 30 degrees Celsius outside. You're saying, I mean, we'd probably say it's 90 degrees here in the States, but, right? But you even say that, you say, oh, it's 90 degrees. When you say the word degree, you're telling me it's a related scale. It's a relative scale. If you say, what's the temperature outside? I could say, oh, it's about 300 Kelvin. So 300 Kelvin, that's the absolute temperature. I don't say degrees Kelvin, I say Kelvin. So that means that outside the energy of the air is equivalent to 300 kelvins of kinetic energy. And then when you say degrees Celsius, well, the temperature outside is 30 degrees relative to the fact that water freezes at 0 degrees and boils at 100 degrees. So I'm telling you that it's related to those concepts. That's what the degree means. And Fahrenheit, actually, some people don't like the Fahrenheit scale. Actually, I like the Fahrenheit scale. It's a very good colloquial scale. Like it makes sense. Like to me, I mean, if I say it's 25 degrees Celsius or 75 Fahrenheit, I can tell. So in 15 Celsius is about 40 Fahrenheit. So to me, it makes more sense to have those grades between 40 degrees and 75. So that's and the reason is the Fahrenheit scale. It was designed to be colloquial. They tried to have it so that human body temperature was 100 degrees Fahrenheit. Of course, that would be a mild fever. Depending on the person, humans are 98-ish, 99 degrees, 98.6, but it depends on the person. 37 Celsius, 98.6 Fahrenheit. But I mean, even that's grades to that. So, but they tried to get Fahrenheit to be 4 points. They tried to get 0 degrees to be the freezing point of brine, 32 degrees to be the freezing point of water, 212 for the boiling point of water. But actually, they really focused it on 32 and 212, and then the human body be 100 degrees, because then that means anything less than 100 degrees would be cold. Well, it would be feel cooler, if you will. So, anyways, but we don't use Fahrenheit in science as much. We do here in the United States. There is an absolute version of Fahrenheit called Rankine. So if you see something and it's about minus 450 Fahrenheit is absolute zero in Fahrenheit. So if you see something that's temperature in R, that's the absolute Fahrenheit. But okay, back to Kelvin here though. And I'm also, I do a lot of volunteer work as part of my job. And one of the things I like doing is judging science fairs. And it's fun sometimes when you get the middle school kids. I tend to do high school mostly, but sometimes I get the middle school kids. And one time this student is like, this got super cold. If you take this line, you go down, it would get to negative 10,000 degrees. You know, and it was so excited that he got this result that's negative 10,000. I'm like, yeah, you can't get below negative 450. Sorry, man. And I'm like, here I am, I'm trying to explain, like, because temperature is actually motion. You can't get any colder than not moving. Right? And he's like, I think I disappointed him. He's like, oh, so it can't be negative 10,000 degrees.
You broke that child's dreams.
Yes.
You stopped and squished.
But it was a teachable moment.
You may have crushed him.
All right, well, okay, back to Kelvin. So, but I think, hopefully you understand what temperature is now. Let me see if you're following. Oh, and I should write the equation. So, Kelvin is degrees Celsius plus 273 So negative 100 degrees Celsius is what in kelvins?
I think it's D. A.
Yeah, I mean, hopefully does everybody see though that it's A? Because you just plug in this equation, you plug in negative 100 plus 273. That's a 4 over 3.
Fahrenheit is like ideal temperature for people. Celsius is like ideal temperature for
Water.
water. And Kelvin is like ideal temperature for atoms. Kind of.
Well, Kelvin, the units of Kelvin and the units of Celsius are the same. Kelvin's just absolute Celsius. So, yeah, and Celsius was engineered based off of water, and Fahrenheit was engineered based off of human comfort. So, we're much better at dealing with cold temperatures than hot temperatures, though. I take 0 degrees over 140 degrees any day. Okay. Other questions? All right. I'm going to skip a bunch of the laws. There's a bunch of them. There's Gay-Lussac's laws. There's Avogadro's law. Avogadro's law says that volume is directly proportional to the number of moles. So which means if I want to blow up a balloon, what do? I put more air, right? I'm putting more air in the balloon gets bigger. So more air means a bigger balloon. That's Avogadro's law. And you can combine them together to form what's known as the ideal gas law. The ideal gas law, and we'll talk about this much more in a subsequent class, the ideal gas, it's a made-up gas. It's not, it's actually a math model. This is a perfect gas that doesn't exist. But at low pressure and high temperature, it works very well. And what we are living in right now, this is considered low pressure and high temperature. So what would be low temperature? Like negative 100 Celsius. What would be high pressure? Like 100 times atmospheric pressure. So like the surface of Venus, that would be high pressure. Antarctica, on a cold day in the middle of winter, would be low temperature. But right here, right now, we are in high temperature and low pressure. So ideal gas law works very well. And what do I mean by that? Well, with gases, some of the things we're going to talk about gases, what an ideal gas is. The ideal gases, they don't have any volume to them. The gas particles themselves have no volume, but the gas has a volume. And that's important. If you compress gases down, then the atom sizes actually start to come into play with the volume. That adds extra volume to it. And then also the gas particles cannot be attracted to each other. So meaning if you can get molecules that hold hands, so they have an attraction for each other and they kind of hold hands in the air. So if you have two particles, it's like having two particles. And if they start holding their hands and moving together, you just have the pressure because there's less volume. Instead of having stuff here, they come together and form one, the volume goes down. And actually, well, that would indicate the pressure would go up by Boyle's law. But by having the fewer particles, it means the number of moles actually of gas go down. So, but anyways, and then a couple things. So P is pressure, V is volume, N is the number of moles, R is the gas law constant, and it doesn't change. R is actually the Boltzmann's constant times Avogadro's number, so it's actually two constants. And R changes based off of units. So, but for this case, it is 0.08206 liter atmospheres over mole Kelvin. So atmosphere, that's the pressure, average pressure of the atmosphere of the Earth at sea level. Okay, so let's apply this. Calculate the volume occupied by 0.845 moles of nitrogen at a pressure of 1.37 atmospheres at a temperature of 315 Kelvin. So ideal gas law, and we're trying to find volume. So the way we find volume, volume is nRT over P. So I kind of like doing that this way. So PV equals nRT if you grab it and pull it there. Or if you want, you can multiply both sides by 1 over P, and then that'll give you that equation. So however you want to do it. I tend to rearrange the variables in my head. That way, kind of using kind of a visual method. Or is that the way you guys do algebra, or do you have to write it out? You do it too? Okay.
I don't do that fraction stuff.
Yeah. Some students need to do it that way.
Some need to be more complicated.
Okay. So volume, we're still moving for volume, and we have N, 0.845, R, 0.08206, liter, atmosphere, mole, Kelvin, temperature, 315 Kelvin. All over pressure, 1.37 atmospheres. I'm sorry, moles. So if you look at the units,
R
moles.
is
Constant.
constant, does not change. So like my affection for you guys is ever constant, right? Does not change.
That's not what you said earlier about grades.
Does not change. Because I'm always happy. So kelvins cancel, atmospheres cancel, and we're left with liters. So the unit being liters, and then put it in your handy dandy calculator.
And the temperature is always in kelvins?
For the gas law, yes. It has to be absolute. You can use Rankine, but you have to have a different R value because the units are going to change. .845, oops, times 0.08206 times 315 divided by 0.37. Oop, that's too many things. 37. Okay. And you get, you get my free ad for using a free calculator. Look at that person.
You've got 36 bits.
Okay, 15.9 liters. Okay. So recap for this one. We want to know the volume. We're given moles, temperature, and pressure. So we use the ideal gas law, solve for volume. Volume is nRT over P. Plug in the values. You make sure the units work, and we get 15.9 liters. Questions with this one? All right. Let's see if you can figure this one out. Pressure is 0.5 atmospheres. Volume is 50 liters. Temperature is 50 degrees Celsius. What is the number of moles? Oops. Okay.
What was the constant? 0.
Oh yeah, sorry.
Your sig figs are off.
It should be 1.5.
2.95. 94.
1 sig fig.
And then that's 0.9.
Oh, I see your point.
Also, shouldn't the temperature be in kelvins?
You have to convert
You
that
just-
yourself. He wrote the equation right there for you.
You didn't take the bait. One of the answers is if you.
3.9.
Yeah, I see your point, but it's
You're not doing
Rounds
sig
up.
figs correctly.
sorry.
These are important things.
It's to have guesstimation. But I guess you've ruined my surprise.
With the kelvins.
Yeah. If you put in Celsius, you get an answer close to 6. But if you put in
3.23.
Yeah.
15.
you blurted out the answer.
I didn't. Peter did.
So there's not really any point in.
I'm just trying to watch my sig figs because 3 of my classes are doing.
Yeah. No, I understand.
Throws me off.
No, it's good you're doing it. It's just I mean these problems are just I'm trying
You
to
do that in your head.
I'm trying to make it fast. So what I'm looking for is if you can do this. And I want to make sure that you know now to use absolute temperature and not the relative scale temperature. So that's what I'm kind of trying to do here. Make sure that you know to use the absolute temperature and also to see that you guys are following this. And I'm sorry, I know that I didn't get a chance to then properly assess you, but does anybody have any questions? Do you understand this and how it works? Does anybody have any questions on how it works? Please let me know, or no, everything good? Okay. All right, my formative assessment. All right, so now we're going to do a derivation, and these are really, I always think they're painful, to be honest with you. Okay, so deriving things. We're going to derive an equation. So PV equals nRT, so start with PV equals nRT. So N over V, this is molarity, moles per liter. So N over V is moles per liter, and to get that, we have to, let me put lines here. So if I want to get, oh, man, this is not liking me. So if I want to get N over V, doesn't want to zoom in, okay. If I want N over V, I have to take V, N over V, and let me put P here, and then put RT. So N, oops, jeez, P over RT. So P over RT is number of moles over volume, which is what it says right there. And if we take N over V, which is moles per liter, and then now I'm going to get rid of that, and I'm going to multiply this by grams per mole, which in this is the molar mass, the molecular weight. I'm going to call this kind of a fancy M, and the units become grams per liter. And mass per volume, this is density. So I can take, so as written up here, P over RT equals N over V. So I can multiply both sides by molecular weight, moles per liter. And as determined before, this equals density. So that means rearranging density is moles per liter times the pressure over gas law constant times the temperature. And that's how you get that equation right there. And before I get in there, let me talk about different temperature units. So we have a couple. We've already mentioned atmospheres in feet water. So 1 atmosphere is equal to 33 feet of water or 10 meters of water. So that's the weight. The weight of 10 meters of water, about 33 feet of water, is the same weight that's in 1 atmosphere from here to about 60 miles up. Same amount of weight. And 760 milliliters, about this much, about 29 inches of mercury is the same. Mercury's density is 13.5 times that of water. So that's why you only need this much versus 33 feet. And also PSI, 14.7 PSI. That's equal to the same thing as an atmosphere. And then we talked about pascals. So 101.3, so 101,300 pascals. The pascal is the same thing as having the weight of about 100 milliliters of water over a square meter. Like that's a really wimpy pressure unit. So if you have 101,300 of those stacked up, you get the same pressure as an atmosphere. And they use these calculations, like they train firefighters with this. So let's say you have a fire that's 100 feet that way. Like if I have a fire that's 100 feet high in a building, how much pressure should I put in the fire hose? And they teach them to be, it's 15 PSI for every 33 feet. So if it's 100 feet up, I'll need 45 PSI. I mean, you need a little less than that, but they just tell them to do 15. So a firefighter comes over there, he looks at the fire, he or she looks at the fire, and a fire truck, another thing, it's a pump. Okay, it has a ladder, has a pump, and also ambulance, right? They have different things. You hook the water line in from the fire hydrant into the truck, and among other things, it's a pump. And if that fire is 100 feet up, I know that I need 45 PSI. So the firefighter is like, that's about 100 feet. All right, we need 45 PSI, and let's get 3 people to hold it. And they turn on it, and then the water will shoot up 15, or it'll shoot up 100 feet. Same thing with plumbing. Okay, so if I need to pump water up a building, so if I have a high-rise building, I need the toilets to flush on the top floor, how much water pressure do I need to get up there? So it's about every story is about 5 PSI, and that gives a story. So 33 feet is about 15 PSI, 44 PSI. So every 10 feet is a little bit less than 5 PSI. So you can do that for having water pump up a building. So that's where the pressure also goes for water pressure for that. And I'm about out of time. I'm surprised my shut-up alarm didn't go off. Okay, shut-off alarm is about to go off. All right, we will pick up here after the test.
I didn't really mean jump off the cliff.
Oh, well, as you can see, I took it too hard.
I was just thinking like, well, horizontally.
Even if he does, we still have a test number.
Yeah, I've already written it in my will that you guys are going to have a test on Wednesday. So in my will it says over my dead body. So I will.
My dead body that's off the cliff.
I will be stuffed and brought in here with a stern look on my face.
Okay, thank you.
You're welcome. Okay.
This is all the homeworks that we need to do, yeah? Like 2, 1, 2, 3, 4, 5.
Yeah.
And how about this one? Is this the test?
Oh, that's just that's the prep you for the semester.
What's that?
That's not the preparation. You're welcome.
Okay, so Do we need to do this also?
Yeah, but do you really don't want to do it?
I don't know. Is it part
Yeah,
of the grade?
it's part of the grade, yeah.
Oh, okay.
Yeah.
So all of this is due on October 9th?
Yeah.
Okay. Thank you.
Yeah.